Thank you. Mhm. Okay, I think this is the second week, and in this case, today we are going to talk about some the architecture hardware um, of quantum computing. Uh, Let me open my window. Okay, uh, basically, we will try to talk about only two most famous one actually. Uh, One of is ion trap and another is superconducting actually. I wanted to put ion trap on top of superconductor. Basically, the main reason is IBM has good amount of resource actually, and IBM is doing very great job to sharing almost all of their contents in open. Even IBM has Qiskit Metal, a software package where tutorials are available. There are people like Slatko Mineb, who is doing a great job. Olivia Lenz, she is also doing great job, and they all are open actually. So I feel that uh, I'm just telling some resources so that if anyone guys are interested, so he or she can just give a look on those uh, resources, and yeah, he or she can manage it actually. But the thing about is, apart from IBM Quantum or Qiskit, I feel that some other resources are not that much available and public. So it sometimes get hard to uh, know about them actually. So basically, that's the reason I placed ion trap on top of superconductor. Basically, superconductor uh, mm, hardware based on a very common thing. It is just a resonator. Uh, Typically in electrical engineer, it is taught in first year. So, but ion trap has some different mechanism rather than the conventional or existing things we read actually. So basically, that's the reason I'm going to start with ion trap actually. And some big companies who are doing whose quantum computer hardware is totally based on ion trap is at this moment there is Ion Q and Honeywell actually. Basically, Ion Q is the most famous one. Then Honeywell is also doing good actually. Okay, so let's start. Just keep this. Okay, so these are the table of the contents. Actually, I will talk about trapping ion is a totally different things actually. Before that, we will go to some band diagrams or energy things actually that is typically taught in solid state device or physics actually, but we don't go into that much deep actually. So this is called hyperfine qubit structure. The ion Q is based on hyperfine qubit structure. So now question is, what is hyperfine qubit structure? This is a very basic common example. So hydrogen has only one electron. That means it has a equal number of proton and equal number of electron. But every proton has its spin up and spin down, and the same goes for the electron. It has also spin up and spin down rotations actually. So the number of combination we can get from here, it is 4 spin up for proton, electron spin up, and we can get for
Hello,
proton
Sakib.
spin down. Yeah,
Sorry to interrupt. Can you please uh, keep it in the slideshow mode? Keep the presentation in the slideshow mode.
is it
If
not
you click
visible?
if you No, no, it is visible, but it will be full screen if you keep it in the slideshow mode. You can click on
Oh, okay.
slideshow after animations,
Okay.
and
Just give
yeah,
me a
and
second.
start from the beginning.
Just give me a second.
Yes.
Uh, I'm not sure, but I think you can help me. Just to help on it. So, uh, I should go slideshow mode. Okay, I'm going to slideshow tab. Then where?
So
From
it is
beginning.
on the
Oh,
top. If you see, yeah, from beginning, if you click,
it is good right now.
um, no, it has not. We can't see your screen into the full screen mode.
Can see my screen full screen. Okay.
Your screen is visible, but not in the slideshow mode.
Hmm. Uh, Interesting. Okay. Just give me a second.
Mhm.
Hmm. I'm once again sharing the presentation. This slideshow. Oh, so you are not getting a full screen. Perfect. Check. Slideshow from beginning. Okay. I'm not sure if this should work, but I'm sharing my whole internet screen.
I think you should share your whole screen to do that. I think not just
Yeah,
the
yeah, not a
application. Share
window.
the whole screen.
Yeah, not a window. I'm not sure if it is good right
Yeah,
now.
now it's right. Now it's come.
Oh yeah, I think from Google Meet, I was supposed to share the whole screen. Okay, internet
Yeah.
screen. Okay, great. Thank you. Yeah, learned a new thing. Yep, great. Yeah, the where I was stopped. Basically, hydrogen has one electron, and it has also a proton. Every electron proton has spin up and spin down. Actually, basically, it's different combination of spin up and spin down. uh, Second, different combination of proton spin up and electron spin down. The energy level of electron is splitted into four ways, and these energy gap actually are totally uh, mm, I mean totally splitted in such a way that is very narrow. Narrow means there is I should say every energy level, it has some top and bottom actually. So there is a top and that is bottom. That's how we get the width actually, width. But the situation is, the more narrower, the more hyperfine it is. So when uh, so our main job is to make it more hyperfine. That means we have to narrow this energy level. So that's the thing. And the question is why this is very much important, this hyperfine qubit structure actually. So that means making this energy level is so much an error actually. The main reason is, let me share how just laser works. It is a very basic thing. There is a electron lower energy level and higher energy level. When we pump it, the electron goes from lower to higher, and but this is very much unstable. Then it goes from higher to lower and it emits some light actually. That's how we get laser actually. So the situation is, in this case, this typical optical structure, we have very large bandwidth actually. So when this is very large bandwidth, it is difficult to control in the sense that there is very wide number of energy level. But every atom excites in a particular energy level. If we can power it up in a particular energy level, So it is good for us because in that case we know that this is the energy I have to power. So basically that's the reason we need hyperfine qubit structure. And another thing is, as I said, this is very much unstable position, so we have to make it stable because we will do some computation for a time being actually. So if electron does go from higher to lower and emits light, so it is vanished actually. So we have to make it happen for a long time. uh, okay, so which are the atoms can be used for hyperfine qubit structure? Mainly those are two electron. uh, those have two electron in the outer shells actually. Basically, all these elements have two electrons in the outer shell. But interestingly, yttrium is used by ion q actually. Basically, I am choosed yttrium because mainly ion q is doing a great job for this ion trap, and I'd like to name a researcher. His name is Dr. Chris Monroe, who is the founder of this INQ. And you will find some good, very much lectures on YouTube or things actually. He was explaining why yttrium is so much good in mathematically actually. So basically, INQ is just ion trap quantum computing hardware is totally based on yttrium. One of the good reason is choosing yttrium is it has the lighter mass actually. Basically, lighter mass, and it shows very narrow bandwidth rather than all those other elements actually. So, what are the advantages of this narrow bandwidth? Basically, we can precisely control because let me explain this chip actually. Basically, it is by IonQ. You can see the blue light glow actually. Basically, these all are ions of yttrium actually. Yttrium 2 plus ions actually. So you see, I think this is IonQ 32 chip. Here are 32 qubits in a same, and these all are in a single line. So let's say I want to control mm, these ion or these qubit actually. So you see there is very much little space in between them. So if I want to power it, like I mentioned, this width of the energy should be very narrow. The more is narrower, the more it will be precise actually, because on that case we can directly hit a particular ion. So narrow bandwidth is very much important. One another thing is, everything has a thermal energy actually. Every atom are, mm, yeah, moving forward randomly actually. Even there is a zero Kelvin, that is minus 273 degrees Celsius. There is a vibrational energy. For that reason, atoms are doing some longitudinal uh, frequency actually, this kind of things. So atoms or ions are totally restless. The thing is, the more lighter the mass, the more we can control to make it a rest actually. So we don't want to delete anything that is moving to and fro actually, but we want to delete something that we have control. So basically that's the reason IonQ choose yttrium. Okay, so now we have ion, we have yttrium. We know why we choose yttrium. Now we have to make it a trap. Uh, it's a good question to the audience. Why we use three-phase AC electric field in our power line? Yeah, I am repeating the question. Why we use three-phase electric field for our power line? Uh, okay. Well, basically, the very basic thing about three-phase or three-dimensional AC electric field is it gives a rotation actually. So we want to use this rotation. So how we want to use this rotation? If we apply electric field in three direction, X, Y, and Z direction, we will get these kind of things. And this yellow ball is our ion, and this is our energy landscape actually. So you see, when it rotates, these ion don't get fall actually, don't get fall. So that's the reason we don't use static electric field, because it cannot trap a ion. This is proven by Earnshaw. But a three-dimensional electric field creates a saddle potential, that means a dip in the energy field or energy landscape, and on that particular energy landscape the ion can stay, because you can see this is the higher, this is the lower. Everything wants to get in lower position, lower energy level, because everything is stable in lower landscape, lower energy level actually. So basically that's the reason three-dimensional electric fields creates the rotation, I mean creates a dip in the energy landscape, and ions are very much stable in there actually, because ion can get a trap position in energy with three-dimensional electric field. Okay, so now we have been able to trap the ion. Now we have to make it rest actually, because ions are restless, they are in vibrational mode. So the question is how we can do it actually. It is something like uh, a common scenario in our daily life actually. Basically, when let's say an ambulance is coming towards me, the more it is coming towards me, the more I am getting higher sound, high pitch sounds. Then when it is passed by and it is moving away from me, and sound is getting lower and lower actually. So basically same things happens to the Doppler cooling actually. So the situation is, this is our ions, this is photon actually. So what we do, like you mentioned, we want to make the energy low. So like the example I just shared, the ambulance should go away from me, so it should be in opposite direction. So this is ion, this is going this direction, and I injected a laser in this direction. So what is happening, laser or photon has an energy, and these ion also has energy. They are making collision. So if they are colliding, so the uh, these has some I mean these has some higher energy actually. So what is happening, they are exchanging energies actually. By exchanging energies, it is losing some energies, and it is emitting a different wavelength. So when it's lose energies, that means when I lose energy, that means I'm getting cooler, I'm getting cooler. And as opposing direction collision is happening, that means ion is getting also slower. Like I said, the lower the temperature, the lower thermal energy, the lower ion is in stable position. uh, so far, do the audience have any question? Mhm. Okay, I'm moving forward. So now we have everything. Now we have been able to control. I mean, we have ions. we are able to we have been able to make it in a rest position. We have been able to make it a trap for it, and now we have to do some computation actually. So one of the very challenging thing about ions, here is 32 ions, and they all are in positive charge. So when two charged electrons are placed side by side, there should be a repulsion. It's very interesting thing. There should be a repulsion. So typically what it should happen, they are repelling to each other and it should throw away from the chip actually. But this doesn't happen actually. So ion should be placed in a line. So now how we can do it actually. So we have to create a ground state like initially mentioned. These are electrons and they have spin up and spin down position. So what I here it is done that the nearby ion is opposite to the opposite to each other actually. So let's say this ion, it has a spin up, this ion, it is a spin down. So these two is canceling each other. The same thing goes for the whole thing. So there is net zero charge. So when there is net zero charge, that means they are staying in there actually. Now I can do my computation in here actually. So typically, like the C note gate we see, uh, mm, yeah, I think last week I mentioned what it is C note gate. For a C note gate, I should have a control qubit, and based on that control qubit, I will have a target qubit, and that will flip the bit. That target qubit will act like a NOT gate actually. I mean poly X gate. But in IonQ case, C not gate does the same mechanism, but we have to prove it experimentally. So the now question is how we can prove it. Basically, Sirac Zoller experimentally showed that it can be done if a laser, let's say I want to make a CNOT gate between this qubit and this qubit. So what I can do actually, you can show that this one is yellow and this one is blue. Actually, basically, that means they are a different wavelength. Uh, can you please guess actually where I have chosen a different wavelength? Uh, any guess? It can be wild actually. Don't worry. It can be wild. Why I have choose two different wavelength? Okay, let me ask another question. Uh, there is 32 electrons. Do you think 32 ions or 32 qubits, whatever you say actually, do you think all the ions are in the same energy level? Yes or no? Okay.
Saying no, they're not in the same.
Why do you think they are not in the same energy level?
Because, I mean, they cannot be in the same energy level, right? It is, or maybe it is because it is quantized. You're saying it's in the same energy level.
Yeah, exactly. That's the thing actually. So it's a very good thing.
Okay.
If they all are in the same energy, let's say I want to control this one actually. So I powered up with let's say two electron volt. So if I want to power it up with 3 electron volt, if all they are in the 2 electron volt, I have no idea which one I'm going to power up. I mean, for which one I'm going to make a computation. If they are all in the same energy, so I want to, I have to make a distinct, uh, there should be distinct energy, because in that case I can control each every mm, qubits actually. So they should not be the same. The energy for every ion or qubit should not be the same. In that case, I'm just injecting a laser power or injecting a photon into the chip. Everyone is getting excited actually. So, oh, just let me power up my. Sorry. Mhm. Yeah, I was talking about power. Yeah. Okay. So yeah, that's the thing actually. So the energy should be the same, and that's the thing. Because this is another. That's why we are using hyperfine qubit structure. Basically, the energy, there is a gap between energy level, and every energy is distinct actually. So yeah, because we choose YOLO because we want to work on this qubit, and we also want to work on this qubit. So for this reason, this has a different wavelength or different frequency to work, and this has also different wavelength, different frequency to work. So that's why I intentionally use two different colors actually. So yeah. So now, as long I have two qubits, now I can do some internal things actually. Basically, this is the basics actually. If you can go to read the paper actually how it works actually, but that's the thing how I can start computing with two qubits actually and make a C not gate. Uh, okay, and yeah, these are some business things actually. This is the position about IonQ, and IonQ has currently I think 64 qubits, and they were supposed to do it in 2025, but they already had 64 qubit. And one of the thing I'd like to share about this, let's say this has 32 qubit. Okay, I want to make, I have to scale it actually, because I want to make a chip for 64 qubit. From there, I want to make it 132 qubit. So the question is, this is a very challenging thing, is scaling, because all the quantum companies are now at this moment in the NISQ era, that means noisy intermediate uh, scaling qubits era. So basically, this NISQ era, those all qubits are error prone actually. But if this is a trade-off actually, the more we have number, the higher the number of qubits, the higher mm, noise happening, and the higher the noise it is, the bad our computation is, the bad results the quantum computer hardware will provide us. So but we have to scale it actually, because uh, I'm not sure if there are any session about quantum error correction. Basically, quantum error correction. I'm not sure if I have shared any example in last class. Actually, I mean in the last week. Basically, why classical computer is still far away from quantum. The main fundamental reason is classical computer has a very less error rate. That means, let's say in my computer, I want to run a program. If I run about 10 to the power 9 times, there is a single chance to make an error. But in quantum computers, so far, current state of the art says if I run it 1,000 times, only 1,000 times, I will get around 30 times error. That is pretty bad actually. So the main reason classical computing is far away from uh, quantum, they had some good error correction protocol. That means they know, those classical computation knows how to correct a error. But in case of quantum, these qubits are very much make interfere with its environment. I mean, it has a very high chance that this ion making interaction with its side ion, and this is making a noise actually. So uh, the point is we have to scale it so that we can make some good computation, we can provide some good results actually. For 32 I have to make it 64. The question is for ion trap, how we can do it. This is very simple mechanism. This is here is one end, here is one end. Let's say I want to make it 64. This is 32 qubit, here is 32 qubit. So what I have to do, I will find another 32 qubit chip, the same as it is. So it will also have the same thing. There will be a two end. So let's say I want to make connect with this end, and I have another chip. I will also make it connect with these two end actually. But the question is, the thing is, every qubit don't have the same energy. These and is not same like the new 32 qubit chip I'm getting actually. So how we can tune it actually or calibrate it so that it feels that, I mean, this chip feels that the new chip is not a different one. This is the same one actually. So what I will do, I will make this qubit energy and the new uh, chip, I mean new 32 qubit chip, the end, I mean the farmost ion, I will make the same energy for these two. So what will happen in this case? These ion and the new chip ion will feel that they are the same. So when these two end will be same, that means they are in continuous. There is no breakout from this chip and this chip. Does it make sense? Or you would like to repeat me? Uh, Hello.
Yeah, you can understand.
It makes sense. Okay. Okay. Great.
Yes.
Thank you. Okay. Great. Uh, yeah, that's the thing they are trying to do, and yeah, every company has its own name. Like Honeywell has some model H1, S2, all those things. Actually, they call it linear restricts, these kind of things actually. And in yeah, and in university level, there are some companies who are working like they are Alpine. There is Infineon. Mhm. Yeah. So basically, that's all about Android. Do you guys have any question about Android? Okay, I will stop sharing. Uh, mm, okay,
So,
so
what kind of work can we do at the simulation level if you're going for this ion trapping? Like,
uh,
is there any
basically,
use also? I mean, can we?
yeah, that's a good thing. I think, like I mentioned, actually, uh, basically, Qiskit is good at publishing these software packages to people. Uh, for case of IonQ, actually, mm, they, yeah, I'm not sure how popular is their software package it is. So basically, if you want to do some simulation of in IonQ, uh, people use Amazon, I mean AWS actually. They use AWS actually. So those are mostly you have to buy it. They are not open. Like you have to buy some credits, and based on these credits, they will give you a connection to their server or to their quantum computer, and then you will write the code for it, and the simulation will happen. Uh, they, I mean, yeah, there is no public access without AWS credit to IonQ actually. Uh, yeah, that's why I said that it's pretty difficult to know about them because, yeah, they don't share everything. They are in hush hush. Yeah, you can do the same thing, but the process is something
Okay.
like they have AWS, through AWS credit. You have to get access in there actually. Yeah,
Okay. Thank you.
so okay. Uh, as I said, that superconducting qubit is pretty much popular. You'll be able to find some resources from there. So what I'm going to do, I will describe some very basic thing. Basically, my apologies that uh, yeah, basically 2 days ago I took my flu shot. I was in bed. Yesterday night I was feeling good, and sorry that I did not prepare a slide for this superconducting qubit, but I will describe it from the Wikipedia page of its very basic things actually. So okay, okay. Before that, um, mhm. Okay, I'm opening a whiteboard actually. So I will share my entire screen. Mm, Can we share? Oh yeah, Jamboard. Yeah, yeah. That's the very basic thing. Like I, and the class was started. Like I said, basically there's the resonator. So mm, it has a capacitor, and I mean in electrical engineering circuit level, introduction to circuit 101 in mostly case, this is taught actually. I have a voltage. Yeah, I have a power. Okay. So the thing it is, this is the capacitor. This is the inductor. Uh, Together, these two things create a resonator. That means if there is a very energy things actually, capacitor has its own energy. The energy stored in the capacitor, it is I think half capacitance, and the power I am going to inject or power I applied, it is in that case as I applied voltage, it is half series. In case of inductor, the same thing. Basically, inductor works on the current going through it. In case of capacitor, it works on the voltage it has between its two sides. So in that case, it is pretty similar as it is capacitor. It is half the inductance value and current going through it, half Li square actually. So that's a very common question actually. Basically, capacitor store electric energy, inductor store magnetic energy, and all of our energy is in I mean electrical or magnetic, because light is a transverse thing of electric and magnetic actually. So we have two fundamental energy is in this circuit. Here is yeah, here is electric and here is magnetic. So that means we have some energy. So when there is energy, we have some Hamiltonian. The when I use the word Hamiltonian, everything is quantum. Uh, you guys will find that Hamiltonian is the thing. Basically, it describes the physical system. It describes the physical system uh, of uh, yeah, of a device or of a thing, whatever it is. So, uh, so that means we have some energy. But the issue with this energy, they are very splitted. Splitted means actually, let's say, uh, energy of these are very much uniform. Uniform. That means energy gap between this energy level and this energy level is same as this one and this one. So in case of qubit or in case of energy, let's say I have an electron in here. So electron will never feel that if it is in this energy level or this energy gap. It will never feel because the energy gap between in these two are same. So it will never feel. So I have to feel it. I have to give a feel, this electron feel that no, you when you are in here, you are in here, when you are in here, this is not the same. This is a totally different thing actually. So how we can do it actually? Basically, this is a linear circuit. In linear circuit, energy is splitted uniformly, but how we can make some mechanism or do some trick. Let's say this energy is so large. Here is, I mean, they are not uniform actually. They are not uniform. So from here to here, there is a wide energy gap. There is, yeah, they all three are not same actually. So when I will place the electron in here, it will feel that, oh yeah, this is not the same. This is different. This is different actually. So like I said, this is a linear circuit. So I have to make a non-linear circuit. So to make a non-linear circuit, I have to find a non-linear device. So what is a non-linear device? I am okay, just mm, uh, okay. I will share the screen once again. Yep. Mhm. Yeah. Now, basically, this Josephson junction, basically the Josephson junction work as the non-linear element actually. So these all three are Josephson junction. Superconducting qubits has some different qubits. Someone is totally focused on charge because capacitor has charge. Someone has some phase. They do some phasing things actually. But IBM mainly use Qiskit type of qubit actually. So Qiskit type of qubit is mean. Uh, Let me explain what is Josephson junction is actually. Typically, if there is two superconducting qubit, I mean two superconducting materials, there is a effect called quantum tunneling effect. Quantum tunneling effect means if there is a energy barrier between uh, if there is any energy barrier for an electron, it pass through this energy barrier means it in classical level it should not go through this energy barrier because it has some barrier, it should not go through this, but in quantum it can go through this is tunneling effect. So Josephson junction is something like this. I have a sandwich things means, let's say at first I have a superconducting material, then I have placed a non-superconducting material side by it. Then I have another superconducting material. So what is happening? Superconducting material. After that, I have a non-superconducting material. After that, I have a superconducting material. Now let's say in the superconducting material, an electron is traveling. So when it will find a non-superconducting material, this is the energy barrier. It should not go through it classical level. But this is quantum. What it will happen, it will go through the non-superconducting material and we will find the electron on the other side of that non-superconducting material actually. So basically it is a sandwich of superconductor material, non-superconductor, and then superconductor. So basically that's the Josephson junction actually. It is something like a transistor PNP or NPN. The call main reason it is called junction, in transistor there is some these N, like say there is P type, N type, or P type. This is a layer, and every layer has some junction actually. So that's why it is called Josephson junction. So this Josephson junction is non-linear element actually. So what will happen in this non-linear element is that we can make this non-linear element actually. Now let me describe this Hamiltonian, how it is. In this, you can see the picture. Yeah, there should be. Again, uh, I'm describing. Okay, I have a capacitor. I have an inductor, and I have a Josephson junction. I have a Josephson junction. So capacitor Hamiltonian is the energy stored in capacitor half CV square. Okay, is anyone trying to say something? Inductor. Okay, I'm moving forward. Inductor energy stored in inductor is this one. Now we have to find the energy stored in Josephson junction. So the Hamiltonian for the whole process will look like this. Basically, this one q square by 2j is for capacitor. This is for inductor, and this is for Josephson junction. We have the Hamiltonians. That means we have the energy. We have the, this is called the anharmonic energy. So this is the squib. Ion Q work based on this simple mechanism actually. So we have Hamiltonian, we have this kind of potentials. You will find this potential, uh, I mean, energy landscape very often. You see these energy gap between these two and these two and these two, all are different actually. So the lower end is ground, and this one is level one. From there, now we can start computation actually. Yeah. Any question? Hello. Uh, okay, I think that's the two thing for, yeah, that's it for today, I think. Yeah. Do you guys have any question?
No.
Okay.
Thank you.
Mm, uh, Srinjoy, in that case, do you, I'm not sure what, uh, you think we can stop
Hello,
here? Yeah.
hello, Sakib. Yeah. We can conclude. We can conclude now, and
Okay.
then yeah. Thank you so
Okay.
much. Yeah. Thank you so much for a brief introduction. I know that this is very brief, but like basically, if like someone wants to understand quantum hardware in detail, then they should be familiar with electromagnetic theory and some basic analysis of analog and digital circuits that actually helps in understanding quantum hardware.
Yeah, those basically, I just wanted to mention some things. So if anyone is interested, they can deep into
Yeah, absolutely.
giving big dive into them actually. So basically,
Yeah.
yeah. So they don't feel intimidated that I should
Mhm.
not jump on it. They feel
Yeah,
that
yeah,
yeah,
of course. Yeah, because
definitely.
hardware itself, as you know, is a broad domain, and it's already an area of exciting research. So yeah, lots of concepts cannot be covered in 1 day or 1 hour. It's a long game actually.
Yeah, like I mentioned, actually, for
Mm.
IBM, they have some very good resources actually. So
Yeah,
yeah, people will can definitely find it actually. But yeah, so yeah, that's the all. I think you will enjoy the next session, and this is going to be great. And have a good week, and be safe, be good, and be energetic. Okay, bye.
Right. Thank you.
Thank you. Thanks for your time.